Alright, let's do Leetcode. One sec. Good. There we go. Alright, so this question I did yesterday was pretty difficult to get my head around, but so I'll try my best to explain how it works. So you're given two eggs, and you want to find out with certainty what the value of f is, and the value of f is the floor number, such that any egg dropped higher than floor f it will break, but any egg dropped below or equals to f will not break. Okay, so for example, if we have 1, 2, 3 floors, so in this case n will equal to 3, we could try to drop on floor 2, so this one here, dropping on floor 2, and let's say for example that breaks. If it drops on, if that breaks, then that means I don't need to check floor 3, I don't need to check floor 1 with the other egg, because I only have 2 eggs, and then I drop it on floor 1, and then if that breaks, then I know the answer will be, I know that f will be equal to 0, because since it dropped on floor 1, f is 1 less than that. And the case that where it didn't break, so if you dropped on floor 2 and it didn't break, that means I only need to check 3. I mean, actually, in this case, I know for certainty it has to be 3, because it's the last one. So the number of moves in this case would be at most 2, in the case that it doesn't break. Then I have to drop 1 on here and 1 on here. And so answer for int 3, if we pass in 3 to this function, would be 2. So let's do it for 1, 2, 3. Do some more examples. So this is, we found out that this is 2. If there's just one floor, it's always going to be 1, right? If there's 2 floors, let's actually look. If there's 2 floors, we could try to drop on floor 2 if it oh, wait a second. If it drops on floor, I just realized the floor 2, the answer might be 1. So I thought it was 2. Okay, let's take a look. Yes, if I try to drop on floor 2 and it breaks, and then try to drop on floor 1, then I have to. I don't know if it's if f is equal to 1 or 0 still. So there will be at most 2 drops. So this will be 2. Okay. So it's very confusing, like, to get your head around, and we can continue this. So for 4, say 1, 2, 3, 4. Okay, so let's try solve this problem using dp, because I mean, actually, let's take a look. It's 1,000, so an n-squared approach would work. N goes up to 1,000. So let's try to solve it using dp. How would dp work though? So we need to, for dp to work, we need to find a subproblem. So for this example, 1, 2, 3, 4, let's say n is equal to 4. What's the subproblem? So yeah, subproblem is actually kind of hard to see. If if we just consider dropping on one floor, so let's say we drop on floor 1, and there are two cases. Either the egg breaks or it doesn't break. If it breaks, then if it breaks, then I know that the answer is 0. And so that's trivial, but so that wouldn't be the answer. I mean, for this case, if I drop on floor 1, because I want to know the maximum number of moves. So we have to consider the case where it doesn't break, because that'll give me more moves that I would have to do to determine with certainty what the value of f is. So we have to assume that it doesn't break on 1, because it's too trivial to assume that it does break. So we assume that it doesn't break, and that means we can use a subproblem on here, because if it doesn't break, that means I still have the egg. I can still reuse the egg. So that means I still have 2 eggs to do on this subarray, and that's size 3. So that means I can use this subproblem here to find out whether find out the maximum value I need to figure out with certainty what f is in this subarray. So that's 2. So the answer would be 2 for here, but I've also already tried this, so that's +1. And so the answer here would be 3, right? So I tried this, which is 1 answer, and then subarray here, which is, I get the answer from here, which is 2. Okay, what about the case? Okay, but that's not the, that was for the case where I tried on this one, try dropping the first egg on 1. But what if I need to consider all possible places I can drop the first egg? So for example here, let's try dropping on floor 2. On floor 2, no, actually it's like the same. So if I drop on floor, say 3, and it breaks. If it breaks, then I only have one egg. If it breaks, I only have 1 egg, so that means the only way to figure out what f is, I would have to try to drop an egg on each of the below levels. Because I only have 1 egg, I need to drop it on floor 1. If it doesn't break, then I have to drop on floor 2. And that's the worst case scenario. So then total number of drops would then be 3 for this subarray here. And I also have to consider the case, of course, if it doesn't break on floor 3, which means I need to test on this subarray here. So it'll be 1 plus whatever this size of this subarray is, which is 1. So it's 1 plus 1, which is 2. So this the right subarray will give me 2, and the left subarray will give me 3. And so I need to try to get the max of the left subarray, size of the left. Actually, yeah, the left versus the right. The right, where the right is equal to the 1 plus the dp. 1 plus the dp of size of right subarray. So let's say, for example, this is j, this position is j, and we have, so that means the size would be n or in this case, let's say the size, this is position I, then we have I minus j here. And the left is just equal to j. So actually, I should just replace that with this dp I minus j. Alright, so then I need to try find the min of this for all values of j. So I'm trying out all levels to see. and this is for dpi. Because I'm just doing, this is for the subproblem of size 4, then I need to find if the subarray is, if the actual problem is bigger, then I would have to find out what dpi plus 1 is, and so on. Actually, let's run through this problem here again using this formula here. So if j is equal to, let's say j is equal to 1, we start j equal to 1, then that means I'm doing the min, I'm doing the max of j, I'm doing 1 on 1 plus dp of, in this case, 4 minus 1, and that's equal to, okay, so 4 minus 1 is going to equal to 3, so that's 4 minus 1 is 3, and dp of 3 is 2, so it's 2 plus 1, which is 3, so it's max of 1 and 3, which is 3. And let's say j is equal to 2 now, so we have the max of 2 and 1 plus dp of I minus j, and I is always 4, that's minus 2, so that's equal to dp of 2, which is 2, plus 1, which is 3, so that's max of 2 and 3, which is still 3. And let's do j is equal to 3 now. So that's the max of 3, 1 plus dp of 4 minus 3, which is equal to, so we're doing the max of dp1 plus 1, which is 2, and 3, so max is 3. And let's do lastly 4. We have max of 4 and 1 plus dp of 4 minus 4. And let's say that means we have to add a 0 here. So that's going to be max of 4 and 1 plus 0, which is just 4. And then taking the min of all these, we get a 3. Okay, so our dp would be a vector like this, of size n plus 1, and let's initialize everything to max, into max. And then we have to go through for all I. What's I? So I will go through starting from 1 to all the way up to I less than or equal to n plus I. And our j will start from 1 all the way up to I, as all the way up to I, yes. So int j is equal to 1, j less than or equal to I plus j, I think. And we need to do the base case. So the base case would be dp of 0 is equal to 0. Let's do dp of, so answer would be dp of I is equal to the min of the max of j, and 1 plus dp of I minus j. And at the end, return dp of n. Okay, so I didn't really check the base case properly, so let's do that. For the 0 here, I is equal to 1, and we have j is equal to 1 as well. So we're doing dp of 1 is equal to the min of the max of 1 and 1 plus dp of 1 minus 1, which is just 0. So that's max of 1 and 1, which is equal to 1. So that also works. Let's give that a go. Should be the min of dp value itself and the max. Okay, so let's test on the largest input they have, 1000. Okay, so I've done this before. I think this is cleaner than my previous solution. Okay, so I get 109 milliseconds. That's quite slow compared to everyone else. So there are better solutions, as you can see down here. So this is an n squared solution, but there is also a linear solution. So if we keep doing this, and it's a bit hard to see how you get the linear solution. But if you keep doing this, you'll find that this is actually 3. And for 5, we get 3 again. For 6, we get 3 again. For 7, we get 4. So you'll see, kind of see a pattern. For 10, we get 4 again. 11, we get 5, and so on and so forth. So you see what's happening? We have 1 1, we have 2 2s, we have 3 3s, we have 4 4s, and it will keep going like this. So how do we utilize this fact? Okay, so what we can do is we could just sum up these values as we go along. So we'll start I from, let's just say that we have a I incrementing 1 by 1. So we have I equal to 1, 2, 3, 4. And as we go along, we accumulate into some value k, the sum of these values. So we can get the sum of these values like, so it'll be 1, 3, 6, 10, so on and so forth. And as soon as, say for example, n is equal to 7, as soon as we hit a value, as soon as k hits a value that is greater than 7, in this case 10, then we return what I is. Yeah, and that's basically doing what, basically utilizing the sequence here. So let's try that. So let's just go increment I, starting from, okay, so I need to use I later on because what I need to return. So let's say int I is equal to, starting from 1, I think. Yes. So I need to say all I is less than or equal to n. Will it ever equal n though? If n is equal to 1, then the answer is 1. If n is equal to 2, answer is 2. And yes, I think I need to go up to including n. And okay, what else do I need to do? So I need to accumulate some value k starting from 0. So I need to do k plus it equals to I, and then say if k is greater than or equal to n, then break, and at the end just return I. Okay, that seems to work. Let's try with 1. And 2. Okay, give that a go. So that's a linear solution. Okay, still quite slow. I mean, it's quite surprising that still it's way better than before though. So there's actually a constant solution to this, and it utilizes this pattern again. So you know how we are summing up these as we go along? We can find any sum in constant time using a formula. So you know that the sum from 1 plus 2 plus all the way up to I, let's say x in this case, is equal to x times x plus 1 divided by 2. Okay, so we know that, let's say for example, our x, in this case our mystery x is equal to 4, and we want the sum k, so if I plug in 4 here I'll get 10. We want the first value of x such that it's greater than or equal to n, because that's essentially what I'm doing here, right? If n is equal to 7, the first value that's greater than n is 10, and that comes from using 4. So if I find x in this equation, then I can find what I is. No, sorry. So in this case, this is a bit confusing. X is equal to this. So I need to find x. So to do this, you could use a quadratic. This is a quadratic if you expand it out. So this looks like x squared plus x greater than or equal to 2n. Okay, but we can simplify that to be minus 2n greater than 0. And so, do you remember your quadratic formula is a minus b plus or minus the square root of b squared minus 4ac all over 2a. Okay, so, and that's for the case where you have ax squared plus, so a times x squared plus b times x plus c is equal to 0. That means if we have this equation, then x will be equal to this, where this is plus or minus, so there's 2 roots. But we just need to grab the positive root. Okay, so our x is going to be equal to minus b. Our b in this case is 1, so that's just minus 1 plus the square root of 1 squared, which is just 1, minus 4 times a times c. A is 1, c is 2n, minus 2n. So minus 4 times minus 2n is plus 8 n. All over 2 and a is 1, so this should do it. This will give us the positive root. If this was minus, of course it will give the negative root, because square root is always positive. So let's give that a go. So let's see what happens if we plug in n is equal to 7. We get minus 1 plus the square root of 1 plus 8 times 7, and all divided by 2. I get 3.27. So x is equal to 3.27. So 3.27 is not really what we want. We want 4. But it makes sense that it's less than 4 because x has to be 3.27 to for k to be around 7. So to solve this problem, all we have to do is take the ceiling of whatever we found here to get 4. So actually, we want ceil of this. Let's do that. Return that. So let's try with 7. Okay, we get that, and you get 1000. Here we get 45. Okay, and this is the constant time solution. And finally, we get 100%. This memory, well, let's just ignore that. There's no way. Yeah. There's no way I'm using that much memory.